Can you hear me okay?
Yes, so there is some wind going on in the background, but otherwise it works.
That is because it is 20. How hot is it here in Celsius? It's like 28, 29 degrees Celsius, and I do not have aircon in my office space, but I will turn that off for the conversation. Should be fine. It's still morning. How are you today?
Good. Where it's not that hot where I'm at. It's 26, 27 degrees Celsius. So warm, but not as bad as last 2 weeks where it was 35. So yeah,
Ooh.
can't complain.
I'm actually looking at my temperature right now. Ah, I lied. I'm at 30 right now. So 30 is pretty hot. And it gets to like 31, 32 in the middle of the day. But it should be okay. Still morning, wind's blowing. But yeah, I think because the conversation's recorded, I don't mind getting started a little bit early. Like I know people will trickle in um, over the course of the conversation. So, probably, larger numbers will pop in a little bit later. But I just, you know, to get things kicked off, I think, just for the sake of intros, just introducing yourself, what you're working on, and I think potentially as well, like how you got involved in BitVM and how you got involved in being one of the co-authors on the paper, I think might be a great way to kick this off, and then we'll dive into the tech side of things.
Sounds good. I mean, there isn't really like this massive story that is, super emotional and, drive people to tears. It's I when the BitVM paper came out, I was actually, going on vacation, so very annoyed that everybody's talking about something and I now have to read up on it during holidays. And in first, I counted myself to the skeptics because the way it was initially presented was a bit confusing to me in the sense that it said, okay, universal smart contract, but actually people interpreted that as, okay, we now can do smart contracts on Bitcoin, whereas it's more of, okay, optimistic computation of prop proofs. And the original paper described a paradigm which initially worked with only two parties, and there was a lot of kind of concerns raised around that. But I got invited into a Twitter space. I think it was the Ordinals show, or where I'm not quite sure. I don't even remember where exactly that was, where you had Robin and Super Testnet, and I was asked to ask them smart questions about BitVM, having spent a lot of years working on Bitcoin bridges. So I had to spend 6 to 7 hours or longer digging through the Telegram group, digging up all these discussions that were happening there and all this additional information that turns out meant BitVM V1, I guess, is practical and actually much more interesting than what the original kind of initial paper that just described the concept suggested. And after surviving that Twitter space and being able to ask a few questions, more questions, I got hold of Robin and then spent a few hours on calls with him where he was so nice to walk me through the BitVM idea and the concept. And then kind of we started jamming on ideas and improvements and practicability. And at some point I suggested, well, we should, it'd be nice to have a paper that actually goes into more detail of how such a protocol would work and specifically how we could do a bridge with BitVM and explain that, step by step from transaction by transaction, input by input to output. So people could then really try to implement it and build on top of that. And that's like Robin liked the idea and we kind of started working it slowly. And halfway through that process with drafts and me making stupid mistakes and Robin kind of telling me, no, that's not how BitVM works. And then gradually kind of also fixing issues and practicability and security risks in the original design. BitVM2 was born. Like Robin had this really cool idea of how we could significantly improve the concept. And we scrapped the BitVM V1 paper and refocused all the efforts to design BitVM V2 as a paper and then following also BitVM Bridge. And over the last few months, we made a lot of progress. Also brought on a research team from TU Vienna, former research colleagues of mine from PG times with Zeta and Matteo Maffei leading that group, as both have spent a lot of years researching Lightning and are experts on that domain, but also like clients and bridges. So naturally, it was a really good fit to work on this together and make sure also that, the security analysis that they're now also adding on top of their first paper draft makes sense, and that the protocol is really safe, and that we can be certain about arguing certain security parameters and bounds. So yeah, that's the not super exciting backstory of the BitVM2 paper. What is more exciting is what it means. It's a significant improvement for like a Bitcoin bridging, and brings us a big step closer to rollups being possible on Bitcoin. So the outcome is more exciting than the process, I guess, in this case.
Yeah, no, totally. So I think before we dive into kind of what BitVM2 is and what the trust minimized bridge design means, I think maybe setting context would be super helpful. You've spent a lot of your research and a lot of your time like on bridges in Bitcoin. So in the paper, you all state in the beginning that all the bridges are currently based on these multi-signature wallets, and then also honest majority assumptions. Like, what are like in your kind of experience, what are some of the designs that you've seen from like federations to things like maybe like TBTC, or even like things like Nomic that have like maybe over collateralization? Like, what are some of the bridge designs that you've seen in the space over like the last 3 to 4 years that have like created this like motivation to build something like BitVM2?
So overall, there is a spectrum of security and practicability, as always, and specifically with bridges. The simplest, like if you look at the far side of the spectrum in terms of, okay, most practical, easy to use, cheap, but not very secure, is, okay, a single custodian. Single person has a Bitcoin. Well, that's not great. And then you can go from there, you can go to, okay, well, let's distribute that trust to multiple signers, and then you get to multisigs. But Bitcoin multisigs usually tend not to be very big because of size limitations. So you can get to, in practice, like 15, maybe 18, 20 signers, and then that's it. So the next step on that journey towards even like further decentralized or distributing trust is to use off-chain signing techniques to multi-party computation models. So threshold signing, like TBTC V2 is using right now, but there's a set of different models like Frost or Janauer and Goldfeller, 18 and 20, the designs that they proposed, which allows us to do even bigger multisigs. So, and that's specifically relevant for Bitcoin and other networks where just, the on-chain costs are a factor, and instead of doing everything on-chain, you have an off-chain computation process where many people can share, work together to produce one signature. So you can scale this to, right now, TBTC has 30 signers, and ideally they're going to scale up higher. And there's also other designers and teams implementing that. But it's still an honest majority assumption, and you need to trust that the majority of the signers are honest. And then we get into this question of how do we select signers, and then some models require signers to stake some third-party token, and you could argue that this third-party token will be lost if the stakers misbehave, and you have some level of additional economic security. And then on the far side of the spectrum in terms of super secure, you have economic security, because ultimately we operate in the economically or financially driven world where our goal with bridges in financial products is to make sure that users don't lose money. And the design, and we actually proposed the first design on the spec, kind of in this direction back in 2018, paper called Exclaim, and the design has been then later used by Polkadot, Cardano, Harmony, Zeus Protocol on Solana. There's a few teams that are using this design right now. And in that design, we say, okay, well, it's over collateralization that ensures security. So instead of trusting a single operator or a multisig with being honest, we say, well, they have to lock up some form of collateral, a third-party asset, maybe the native asset of the chain, so like ETH. And this can be restaked Ethereum, something that's already earning yield for improved capital efficiency. But ultimately, you have additional collateral, additional stake locked up, and that stake in terms of value has to exceed the value of Bitcoin deposited into the bridge. And as long as that holds, there's no incentive to try to steal the Bitcoin. We don't have to worry about any complex custody models. So if I'm the operator, I locked up, let's say, $10 million worth of ETH, and then you can deposit, let's say, $7 million worth of Bitcoin with me. And if I try to steal the 7 million, I lose 10. So the math is quite easy. This is very secure, very easy to implement, but not very scalable at all. It's very expensive. You have to essentially make up for the capital costs of the operators. You have to come up with smart ways of restaking that collateral and reusing it in DeFi to generate yield, so that operators have additional incentive, actually have incentive to deploy their capital to run the bridge. And with restaking protocols like EigenLayer, this might be interesting, where we see more and more rehypothecation of tokens like Ethereum, but again, by far the least scalable design. And then, of course, you can combine the multisigs with the economic design, where, as discussed before, you have some fractional staking where you only have like 10% of the value is kind of backed by some stake. And there's also a bunch of other things that people have tried with, adding hardware security on top of the signers. So there's some hardware devices that make it more difficult to break into the device, into the machine, and make it more difficult for a person running the node to try to get the node to misbehave. But these are all additional layers of security, which are great. But at the end of the day, if we zoom out, their spectrum is either you trust one or multiple people, and the majority has to be honest, or you don't trust them, but the model is purely economic, like purely based on economic security, and it's very expensive in terms of capital requirements. And that's where BitVM makes a major leap towards a mix of security and capital efficiency. With BitVM2, we have a model where out of a set of n parties, where that n can be, I don't know, 30, 40, 50, you only trust one. So one needs to be honest. And this is called existential honesty. There exists one honest person in this set to ensure security of funds. And that's what BitVM gives us, which is a very nice balance between security and capital efficiency. And again, makes it much more attractive to build bridges that follow this design.
No, 100%. So like looking into a lot of these designs, you do have that kind of that trade-off spectrum of where like, are we going to trust this like alternative monetary asset, for like potential over collateralization and slashing, etc. But that seems to be, from my vantage point, everyone who's tried to do that so far has kind of changed the model somewhat, just because due to the inefficiencies of running that type of bridge. And then you have the federation side where you're just trusting like an honest majority of signers. So neither of these are ideal. And something you mentioned in when we were on a panel in Nashville is like we just want to be able to be competitive with other ecosystems that have access to these like trust minimized bridge protocols. I think building on that, something I want to kind of ask is, this bridge design is a little bit different in the fact that there's also this idea of like permissionless challenging. So correct me if I'm wrong, but I read the rest of the paper last night. It's my understanding that anybody can act as so you have like a predefined set of operators who are operating the bridge, and then like anybody with like sufficient capital requirements can participate as a challenger in submitting a challenge transaction if they think one of those bridge operators is dishonest. Is that the current design, and what was the motivation? And if that's the current design, what was the motivation about expanding the challenger set and having more people be able to participate in that?
So one of the cool things about BitVM2 is right that you can allow anyone to trigger this challenge, which means that if we dissect the security model of BitVM2 a bit more, you generally, when talking about security of distributed systems or protocols in the blockchain space, you talk about liveness and safety. Liveness means that things progress, transactions happen, like eventually something will happen, right? Eventually this thing will stop, and like we'll let in the bridge, you'll get Bitcoin out or Bitcoin in. And the other property is safety, which we generally care most about, which means funds cannot be stolen. And there's a subtle difference between the two of these, is that in a liveness failure, if I as an attacker can cause a liveness failure, I can freeze funds, but I can never get money from that because I cannot steal the funds. And in a safety failure, if I break safety of the protocol, then I can steal the funds and I make a profit. And in generally speaking, in things like multi-sig bridges, these properties are the same. You need an honest majority of people to ensure safety, but they also need to sign to ensure liveness. So if I have a multi-sig of 5 out of 10 people, or 6 out of 10, let's say, I need 6 out of 10 to move funds under any circumstance, whether it's good or bad. So I need 6 out of 10 honest majority for liveness and safety. With BitVM2, we split these properties up. For liveness, we need that one honest operator. So let's say you have a set of 50 operators, and we need one of them to be honest and online, in the sense that if we challenge operators, right? If an operator is malicious and dishonest, we can challenge them and we kick them out. But we can do this only as long as there are operators left. So if all of them are malicious, all of the 50 operators are bad, then the system, of course, breaks. And yes, we can, and that's the cool thing on BitVM, we can kick them all out. We can prevent them from stealing and breaking safety and making money, but we still end up with a liveness failure where the Bitcoin are stuck because there's no operator to actually complete the withdrawals, because they were all malicious, they all tried to steal, all 50 people colluded, and we prevented them from stealing, but we still have the funds stuck. And that's not a great scenario, but it just takes away the incentive to attack. Whereas in many other designs, if you collude, it's much easier to get an honest majority than to get everybody to collude. And that's the cool thing about this existential honesty assumption. As long as there's at least one honest operator in the BitVM set, we know that the funds will definitely get back to the users. And if all of them fail, okay, well, the funds will be stuck, but the operators won't get anything out of it. They will not make money. So there is no incentive for them to try to collude and attack the system, because they cannot, even if all of the 50 operators collude, they can't steal. And that's the cool property of BitVM. Yes, in theory, all the 50 or whatever operators can collude and shut down the bridge, but they make no profit, and hence there is very little incentive to do so, because attacking the bridge is also associated with some cost. Whereas, and that's what permissionless challenging achieves. So anyone can make the challenge, and that allows us to ensure that operators simply, if they are rational in any form economically, they will not try to collude and cheat, because they know that they will get challenged. Every single one of them will be kicked out. User funds will remain stuck, but they cannot be stolen. Okay. And that is, it sounds still like there's always risk associated, but this is by far the most secure bridge design in practice.
No, I would completely agree with that. I think creating this system where anybody can ensure the integrity, or ensure that funds are at a minimal not going to be stolen, at a minimum not going to be stolen, is by far the most superior design we've seen, kind of being presented and being developed at this moment in time, that doesn't require a soft fork. And I think something I want to touch on, though, is with the permissionless challenging side of this, right? This does sound similar to an optimistic assumption. And you mentioned earlier that this allows us to give us the ability to have optimistic rollups on Bitcoin. Can you kind of dive into the nuance? Because, in the beginning of the paper, it states that we're building the snark verifier. What is kind of the nuance here of this, being an optimistic rollup but has ZK optimizations? Just wondering if you wanted to touch on that, because I know that this is something that you've talked about in the past.
Absolutely. I mean, I think we all agree that, ZK, right, this ZK rollups are the future. The fact that they're so efficiently compressed and allow us to prove on-chain that something happened off-chain that will be otherwise too expensive to execute on-chain is a brilliant way to design highly scalable distributed systems for payments and smart contracts. However, on Bitcoin, right, we can't implement, as of today, a ZK verifier in Bitcoin script. What many people don't know is that we can implement it in Bitcoin script itself, right? The problem is that a snark verifier, as of today, based on the current state of the implementation, is 2.9 gigabytes in size. So no way to get this into a Bitcoin block, right? The Bitcoin block size limit is 4 megabytes. Plus, there's also the stack size limit of how many items you can put on the Bitcoin stack, like in the program when you execute the program. But let's just focus on the block size for now. So we have this big snark verifier. So why do we ever even bother with a snark verifier in the first place? Well, the cool thing about a snark verifier is that it's constant in size. So if you manage to take any form of program and to compile it and compress it into a snark verifier, so that you basically only need to check that. So you get a verifier that tells you, okay, did this program run correctly or not? And the cool thing is that this is constant in size. So even if the original program is much, much bigger, hundreds of gigabytes in Bitcoin script, if we can compress it into a snark, then it's 2.9 gigabytes in Bitcoin script, which is very cool. So now we only need to figure out how do we get these 2.9 gigabytes of Bitcoin script into a Bitcoin block. And here we have two options. One that requires a soft fork, meaning introducing covenants, opcat, or something else that may allow us to reduce the size of that program, implement it in script. And you can think of this as if you're familiar with Solidity and like Ethereum or like programming overall. When we write programs, we have a set of libraries and tools that we can use, like multiplying to numbers, concatenating to strings. And the thing is, Bitcoin script has a very limited set of those. So you have to implement everything yourself from scratch. And with OPCAT, you basically can emulate a lot of covenants, and that just allows us to reduce the size of the program. So think of it as a pre-compile on Ethereum. Instead of implementing your own kind of function, you can just use existing tools. Like, that's overly simplified, but basically it allows us to compress the size of the snark verifier to potentially being able to fit it into a block. Question mark, unsure if that will work. We've seen early prototypes, and with Circle Starking, we can actually made a cool presentation. I'm not sure if he's listening in or not, but it's still going to be very expensive. And not every rollup will be able to afford this, specifically with the high costs that we anticipate on Bitcoin L1 for fees. So the other option is to do this optimistically. Just say, well, okay, let's run this program off-chain. And if we all agree that it was run correctly, okay, well, then we don't need to do anything. We just say, okay, we're perfect. No on-chain footprints, very cheap to do in the happy path, which makes optimistic rollups much more efficient than ZK rollups, because in a happy path, you don't have any on-chain costs in that sense. The disadvantage of this approach is that we have to use prop proofs. So this means that when you announce, let's say that you as a bridge operator have done a correct peg out from the bridge, there's a 7-day challenge period where anyone can challenge you. And that is, of course, a disadvantage, because with a ZK rollup, right, if we actually can execute the verifier on chain, we know instantly that everything was done correctly. In the fraud proof design, you have to wait for 7 days. So that's the two design trade-offs. And on Bitcoin, we anticipate that mainly people will use fraud proofs. Because we don't yet have OPCAT or other covenants yet. So by design, it's currently not possible to implement a snark verifier in Bitcoin script that fits into a Bitcoin block. And because even if we could, it would still be very expensive. So using BitVM-like designs will likely be what we see used in production most. Now, honestly, I forgot what the original question was, so I'll pause here so we can get back on track.
No, I think you pretty much covered it. Like, we're trying to there's just efficiency. There's an efficiency side of it using the fraud proofs and the optimistic side. But I think, yeah, the question is, like, there is this kind of, like, I had a conversation with someone about this yesterday. There's this kind of nuance to where, like, it's an optimistic roll up, but it does use it does use validity proofs to improve the efficiencies and the optimizations and the performance, etc. So there's this weird nuance where it's kind of a little of both. And I know that's always going to be a hot debate when things like this come into production and people start claiming one thing or the other. So it's going to be very fun to be a part of that discussion. But yeah.
But I have to go on record and say this. You know me. It's not a ZK rollup as we know them from Ethereum. And I think it's always dangerous for us in the Bitcoin community to come up with our own definitions and terminology that is used for things that are for different things in, say, the Ethereum ecosystem, where a lot of the original ZK like rollup designs have been conceived. Because what an Ethereum user understands under ZK rollup is, okay, the ZK verifier is executed on chain fully, which in Bitcoin with BitVM, it is not the case. And if we come from an Ethereum user's perspective, and ultimately the entirety of the Web3 space outside of maybe core Bitcoin right now, optimistic rollup is defined as, okay, we execute off chain, and if something goes wrong, we challenge, and that's what BitVM does. And even if we use the snark verifier for compression, it does not change the fact that the security is an optimistic model, and it is confusing and unfair to users to call these things ZK rollups. Yes, we can debate from academic standpoint that, of course, there is a difference between, state transition and we can be posting the proof data to Bitcoin so that we can read that data from Bitcoin. Anyone can read it and verify that the proofs are correct. But as long as we don't fully enforce across every Bitcoin full node, always, not optimistically, but pessimistically, that these proofs are correct, it's dangerous to call it a ZK rollup, because the majority of the population that is familiar with the rollups understands something different under that nomenclature. And hence, that's why I will always go and fight with people about this, because I just feel it's risky and damaging for our Bitcoin community to call something a bit ZK rollup, which clearly everybody else understands as an optimistic rollup, even if we do use this ZK compression. And what you see, like even on Ethereum, you have, for example, optimistic rollups with ZK fraud proofs, right? Where they use ZK compression to make the fraud proofs more efficient, which goes in a very similar direction of what BitVM2 does, but they still call it optimistic rollups with ZK fraud proofs. And I'm a fan of calling things of just what they are and not, introducing fancy new words. So again, I just have to go on record and say that, because I do feel strongly about this topic.
Yeah, and I think from an academic perspective, like I've heard two different sides of the debates. It seems like from my vantage point, a lot of people that are kind of on the sovereign roll-up side will very much argue in kind of favor of this being like a sovereign ZK rollup with an optimistic validating bridge. But I think when you get into that like length of like defining something, I think it does kind of maybe cloud some of the nuances within that, and it might give users kind of a different idea of how these things compare to maybe potentially rollups in Ethereum, where I think most of the Ethereum landscape or people I've talked to with regards to like BitVM, BitVM2, etc., would definitely agree with kind of the sentiment that you've given there. I know we've got about 15 minutes left. There's two questions I want to ask. The first one I think we can go through pretty quickly, and it's just a general question. A report that we helped Galaxy write on data availability came out, kind of basically saying that long term, roll-ups are going to be very like expensive to do on Bitcoin, just due to the like limited throughput that Bitcoin has and the amount of data that's available every 10 minutes, and that it's going to be kind of like this fight to get your sequencer, your transaction data into a Bitcoin block between all these rollups. So a lot of people might opt to use like alternative data availability solutions, so maybe like a federation or a other DA kind of specific blockchain like Celestia. I know the paper focused solely on rollups, but what are you thinking through, like, what is your kind of like, I guess, general idea through the trust assumptions that Validiums or Optimiums or whatever you'd like to call them will have with BitVM2? Like, what are kind of the trust assumptions there? Is it just that the operators of the bridge additionally need to run like a data availability like client? Like, what's kind of the trust assumption there versus like having a chain where all the data is posted to Bitcoin?
I think this really depends on, what will the Bitcoin fees look like. And I debated Udi about this, and he's like, well, why do you think Bitcoin fees will be high? It could be zero. Of course, it could be zero, and then it's not a problem. Of course, we all anticipate that Bitcoin fees won't be zero, and there will be high chances that they are not zero. And also, if we assume that they're low for our security model, and then naturally somebody who has resources, not necessarily on the mining side, but just money to burn, could just spam the chain You can coordinate this, you can span the chain exactly in a period where you're attacking the rollup, and then if the rollup has to get the proof in and post all the data to be operational, that becomes very expensive, and you can execute denial of service attacks. And you've seen this on Ethereum, where basically, there was a soft fork or a fork introduced actually that makes it cheaper to store temporary data on Ethereum full nodes, and this data that we would use to generate proofs or fraud proofs, right? It's cheaper and it's temporary. You don't need it for the whole kind of eternity, and that is something that Bitcoin currently doesn't have. So I would expect, and I would operate under the assumption that the fees will go higher. Right? Let's assume that's the case. Let's work under generally a pessimistic model where it's good for Bitcoin fees to be high because Bitcoin is used, right? But it's bad for protocols that post data to it. And when you design security systems, you generally assume that what's the worst case scenario, and then you try to make a system that's secure. So if we assume that scenario, and as the Galaxy report suggested, well, it's going to be very expensive for rollups that want to post data to Bitcoin to actually sustain operations. And we're talking about millions of dollars of revenue that they would have to generate from the start, unless you can get funding to cover all these infrastructure costs. But then suddenly running a rollup on Bitcoin becomes so much more expensive than running a rollup on Ethereum. So why would anyone do that? And that is always the thing that I urge people to think about. We're not in an isolated world where everybody wants to build a rollup on Bitcoin and use a rollup on Bitcoin just because it's Bitcoin. No, we're moving into a world where people want to use Web3 services and they don't want to worry about necessarily where they're built on. It's easier to use Bitcoin as a way in because Bitcoin is so globally adopted, people trust it, people know it, but they won't use it if it's 10 to 100 to 1,000 times actually more expensive than using an ETH rollup. They just won't. If your service is 10 or 100, and we're actually not speaking about 10x, we're speaking about 100x plus more expensive than another service, your service has to be so much better for people to pay for it. And realistically speaking, the innovation space for rollups themselves is limited, right? You can have very cool applications, but it's not defensible. What prevents somebody from just copying that application onto an ETH rollup or a rollup that does not post data to Bitcoin for the whole time? And maybe it makes a trade-off between security and usability. And I tend to wear the pragmatic hat here and say, well, look, there are other models where we can inherit some Bitcoin security for the D8 layer using something like merge mining or having chains that use Bitcoin staking, right? These are side chains where we just store that data. And yes, we have to figure out a way how to read the data from these side chains. And even in BitVM2, we do say that, okay, well, the design assumes that we have rollups that post everything to Bitcoin, but explicitly and that's also where our focus is from the Bob side, are trying to look into designs where the live client works for also other consensus protocols. And merge mining and Bitcoin staking here are two protocols that are close to Bitcoin itself, use similar primitives, and hence are easier to verify. And I generally anticipate that, yes, there will be some additional trust assumptions than only Bitcoin being secured on the DA layer. And we can get as close as saying, okay, the majority of Bitcoin staked, right? There's like billions of dollars of Bitcoin staked that secure this DA layer, or there is like 80, 90, 100% of the mining power that is participating. But it's not exactly the same because not every Bitcoin full node has it. So I think we can get very close and have a nice and acceptable trade-off between being very, very secure and building for ethos, but not being usable at all, and this whole kind of thing not working or not being used by anyone, versus being efficient, fast, and actually competing on the product side and still having a very high level of security.
Yeah, no, that makes sense. And I think there's also like additional things you can implement for like there's some cool tricks that you can do with these light clients that can make alternative data availability systems a bit more secure. But for the sake of time, we don't have to dive into those. Something that I know that we talked about before and I thought was quite interesting was kind of your opinions that like a lot of these potential soft fork proposals don't necessarily compete with BitVM2. They can actually make it better. So I think kind of understanding, what do you think is something that a lot of them are being discussed right now. So you have like great script restoration, you have like OPCat. I think a lot of people are still talking, a lot of people are still discussing potentially using CTV. Like, how do these things, or how might some of these things help improve the trust assumptions or the performance related to BitVM2? And why are you kind of on the stance that these things are actually a lot more complementary than we might see on Twitter, or we might see like in like online discussions about this stuff?
I mean, I know, like, so the way that BitVM1 was designed was like it was clunky and it was hard to use, and it was the first version, and like Robin clearly stated that by now the design of BitVM2 is the one that people should follow, because the previous design was indeed very hard to use and had limitations, and a lot of the white papers that were released around BitVM1 or building on top of that, optimizing it, they still are very far away from the efficiency of BitVM2, and we expect a lot of the teams that have been working BitVM to start using BitVM2, and that's why also we released the paper for everyone to be able to use, versus as Bob trying to do our own little thing. We believe that BitVM needs to happen, and we need to get rollups on Bitcoin. The easiest and the best, well, the most reliable way of doing that is being collaborative and just contributing to the canonical version, you could say. Now, where was I?
How we can potentially optimize BitVM with a lot of these software.
Thank you. Yes, thanks. Long day. So there is a nice little section at the end of the paper, and with a soft fork, I mean, ultimately we can debate which opcode we should introduce, and people argue for OPCat because it was already in the Bitcoin code base, and then other people argue yes, but Satoshi they removed it. So you can spin it both ways in terms of the marketing side of things. However, let's assume OPCat, right? Let's assume we get that. The cool thing with OPCat is that you can emulate a bunch of different opcodes and covenants. And from the BitVM perspective, what this gives us is, A, we do not have to emulate covenants. One of the challenges of designing a system like BitVM for bridges is that when we bridge Bitcoin in and we send it to somebody else, we don't know who will be the person that is withdrawing Bitcoin back. We don't, simply. And for this reason, we need to make sure that the operator, basically, so the only way to do this in Bitcoin is then to say, okay, we fix the set of people that can withdraw from BitVM, but we still want to make this fungible for everyone. So we just make sure that the operator has to send Bitcoin to whoever is withdrawing from the bridge, and then they reclaim Bitcoin from BitVM. So you guarantee good UX for users, and the operator, who is a professional that makes money on this, they have to put up some temporary capital to fulfill withdrawals, and then they can always reclaim within a short period of time the BTC again from the BitVM bridge deposits. Now, we need to be able to challenge these transactions. If the operator is misbehaving and actually did not send Bitcoin to the right person or tries to steal, so there was never a peg out on the sidechain and the operator is just trying to withdraw from BitVM without ever processing something in that direction, we need to be able to challenge. And for this reason, we currently need something like covenants. And either we can determine how a specific transaction can be spent in the future. So we need to make sure that when an operator tries to withdraw from BitVM deposits, we can challenge it. And without covenants, we need to use pre-signed transactions. So we at setup need to have a committee. And that committee is of size n. So we can have 100, 1,000 people coming online once for the setup of every BitVM instance, signing a message, signing a transaction, and then they never have to come online again. And the only thing they need to sign, the only reason we do this is that we have Bitcoin going into deposit accounts, which is controlled by, let's say, 300 people. And as long as one of them destroy their keys, nobody can ever spend from it. So it's an N of N multisig. And then we have a set of pre-signed transactions for each operator that allow them to spend the deposits in a certain way. And this way we can ensure that these transactions that are pre-signed can be challenged. So very technical explanation, but that's essentially one of the main crux behind Bitcoin scripting. Bitcoin smart contracts work differently than EVM smart contracts in that case. And with covenants, we could get rid of this. With covenants, we would not need to emulate covenants, right? So we could get rid of that setup. We would make it much easier to design. And what we could also do is we could replace the snark verifier with the stark verifier, which has very nice cryptographic properties. And last but not least, also we could reduce the size of these challenge and disprove transactions. Specifically in BitVM2 right now, you need 3 transactions to complete the challenge. First, if I'm the malicious operator, someone from the audience could be a challenger, you make a challenge transaction. That's a normal Bitcoin transaction, not expensive at all, very easy to do. Then next, I have to respond by publishing the so-called assert transaction, where I reveal the intermediary results of my computation. And that transaction is 4 megabytes in size, so it's a full block. That's expensive. And it's a hassle to include it in Bitcoin, so I need to send it to the miner, but I have to do it, otherwise I lose as an operator. So even if I'm honest, I get challenged, I have to respond. Which is why in our design, we assume that the challenger crowdfunds the costs of this transaction and pre-funds it for the operator. There's some game theory designs that we can explore. Let's ignore those for now. And then the last transaction, if I was indeed wrong and I was misbehaving, the challenger, or again, any other challenger, can then execute the disprove transaction, which again is large. It's up to 4 megabytes. And with something like OPCAT, we can reduce the size of these transactions significantly, which reduces the costs of executing a challenge. Now, what I noticed is that throughout the entire space, we actually never discussed how exactly BitVM2 works. So I don't know if it makes sense for me to give a 30-second TLDR of the high-level idea, because that also explains why we have 4 megabyte transactions involved in the process. What do you think?
Yeah, go ahead. I think we definitely covered stuff on like the bridge side, but yeah, I think the overall idea, yeah, go for it.
So the idea we discussed, right, that you can implement anything in Bitcoin script, but these programs are very big, and if you want to execute them optimistically, the way we do this in BitVM2 is we take the program, we compress it into a snark verifier that is still too big, right? It's 2.9 gigabytes. And now we split that verifier program up into sub-programs. So we say we take the 3 gigabytes and we break it down into sub-components, sub-chunks of programs that can be executed one after the other to get to the same result. And we design them in a way that they're sequential. So if you have a program F, that is the ZK verifier, the snark verifier, that is 3 gigabytes in size, what we then do is we split up into F1, F2, F3, F4, so that if you execute them one after the other, and F2 takes as input the result of F1, and F3 takes as input the result of F2, and so on. So you have to execute them one by one. Then you get to the same result. They have the same snark verifier. Now, each of these programs is 4 megabytes in size at most. Why? Because then we can actually run these individual programs in a Bitcoin transaction. And what we do then is the operator commits to running this program using taproot trees. And as mentioned, because we have to emulate covenants, we have some pre-signed transactions involved. And then when we run the bridge or whatever other program we might want to implement in BitVM, if the operator misbehaves, then any user can challenge the operator. And this is a normal transaction as discussed. And as a result, the operator has to respond. And the operator has to respond by revealing the intermediary results of these programs that the operator executed. So I have to show the input to the program and then the result of F1, of F2, F3, F4, up until the last subprogram, and then the final result. So you now have the start, the input, the output, and all the intermediary results of all the programs that I was supposed to run. You know what the program should look like because I committed to these programs at the start. So now on your local machine, if you run the same snark verifier, you should get the same intermediary results. Now, obviously, if I cheated, the only way I can cheat is either I'm just blatantly cheating and I'm not going to show any computations and I ignore the challenge and then I get flashed. Or if I'm trying to be smart about it, I had to change that snark verifier somewhere. Let's say I replaced the withdrawal address, so it's always mine. So I never send Bitcoin to users, I always send it back to myself. So somewhere in some one of these programs, F1 till FK, let's say, right, there's K programs, could be 1,000. I changed it. So now the result is different. So the intermediate result of that program will be different to what you will all get on your local machines. And now the cool thing about this design is the only thing that any user needs to do is to go and run that specific program where the operator has a different result than you see on your local machine. And you just run that specific sub-program that is 4 megabytes in size at most in a Bitcoin block, and you show that the result is not what the operator claims it to be. And that's it. And that's enough to then slash the operator. And specifically, we invalidate the transaction that the operator was supposed to use to withdraw funds and permanently kick them out of the operator set, making sure they can never try to access these funds again. And that's BitVM2 in a nutshell. So we compress a program, we chunk the snark verifier up into smaller sub-programs, operator commits. When we challenge, the operator gives us the intermediary results, and then we challenge by running one of these programs and showing that the thing that the operator claimed to get as a result is different to what we actually, everyone now on the Bitcoin network can see. That's it. It's a very simple concept per se. The tricky bit is implementing this in Bitcoin script.
No, totally. And I think that with the recent paper kind of coming out and improving on the design and essentially also adding like that permissionless challenging factor, I think is going to be like super exciting to see people iterate on this and then look to implement it. And I agree with you, like a point you made earlier, it's like the more people that we can get kind of collaboratively working on this together can help, I guess for lack of a better term, what's the word I'm looking for? Can make the design more bulletproof, can help it get to market faster, can create a more secure implementation. So I'm really hopeful to like see the collaborative nature of the space take over and help move this thing forward. I think last question, what's the plan for Bob? Like, what are you guys planning on? Like, I don't imagine you spent a lot of your time on this if you weren't interested in potentially implementing it on Bob. So is there any like potential future design where you guys look to implement something like BitVM2 as a bridge between your chain and Bitcoin? Just curious, for future plans there and what you're thinking about this from a go-to-market perspective.
So the vision for Bob and is to run as a hybrid layer 2. So the design of a hybrid L2 is such that we can inherit security from one network. In this case, it will be Bitcoin using BitVM2 and then using BitVM bridge to have this arguably almost native Bitcoin bridge where, again, as long as we have one honest operator or somebody challenges, we can always get the Bitcoin out. So just the same thing that ETH rollups call native bridges to Ethereum, we have a very trust minimized bridge design where people can deposit Bitcoin into Bob and use it and always or almost always, right, get it out. That offers a much better security model than any centralized platform and basically really gets us towards a world where Bitcoin can do smart contracts, but it's still secure. But we also are pragmatists and we accept that a lot of the innovation comes from Ethereum. A lot of the new things happen in Ethereum land. Bitcoin and Ethereum together make up 95% of the market. And right now, Bob launched as an ETH rollup for exactly this reason. BitVM doesn't yet work in production. So we prefer to inherit security from Ethereum, which is number 2. It's good enough for billions of dollars worth of capital to be used in DeFi and other products. It's good enough for Bob initially. And then once we get BitVM2 and BitVM Bridge to production, what will happen is that the fraud proofs that are currently executed on Ethereum are replaced with fraud proofs on Bitcoin. So our security model then becomes Bitcoin dependent. And the difference between us, I guess, and many other Bitcoin L2 designs is that we want to keep that native bridge to Ethereum. So what we do is we modify the Ethereum layer 1 contract that previously would accept fraud proofs on Ethereum to show that something went wrong on the Bob rollup to accept fraud proofs that happen on Bitcoin. So now we are all like both Bob, BitVM, but also like Ethereum, the L1 contract and Ethereum are looking at Bitcoin to see if a fraud proof happened. This means that as an ETH user, you're now trusting when you deposit your assets into Bob that as long as there is somebody who'll do a challenge on Bitcoin, you'll be able to get your assets out back to Ethereum for ETH and your C20 tokens. And the cool thing is that Ethereum can easily verify Bitcoin transactions using a Bitcoin-like client that has been implemented for years. We built optimized versions of it. It's running in production on Bob. There's TBTC that's using one as well. And the cool thing is now we have Ethereum users that can bridge into Bob and use ETH and ERC20s with Bitcoin and DeFi, and they can always get back. And the vision here is that we invert the design so far. So far, people have to ramp Bitcoin and go to Ethereum and to DeFi or Solana or others to use Bitcoin and DeFi. What we want is to inverse this. Now, in the future with hybrid designs, we were the first to announce, but then Starkware announced something similar, Tron announced something similar. We'll see much more of these hybrid models emerge in the future. With this hybrid design, we can say, well, look, Ethereum can verify Bitcoin security, so why don't you just bridge to Bitcoin? And Bob is one of the places that are secure by Bitcoin where you can use your ETH and ERC20s in DeFi with Bitcoin, because Bitcoin is the biggest thing, has the most liquidity, is the largest digital asset. Why not invert this? Go deposit your ETH and your ERC20s into Bob, and you'll always be able to get them out as long as Bitcoin is secure and somebody can challenge. And the cool thing is this works for any smart contract chain. Solana, Tron, Sui, Ton, whatever, anything that has smart contracts, as of today, can verify Bitcoin transactions, meaning they can verify prop proofs on Bitcoin, meaning they can bridge assets and deposit assets into Bob and always get them out as long as Bitcoin is secure, as long as we have the prop proofs on Bitcoin. And the vision here is that we can one day replace centralized platforms, because if you think of centralized exchanges, they are the original layer twos. They connect to multiple different chains and offer you a way to deposit your assets, trade them, use them very efficiently for low fees, but you trust the centralized exchange. And with this hybrid design of Bob, we can use Bitcoin security and get all of these other chains to deposit their assets into a Bitcoin secure platform, which is transparent, which is censorship free ideally, and you can get your assets out always, as long as Bitcoin is secure. And that's, of course, where BitVM plays a massive role in Bob's roadmap. Is without prop proofs working on Bitcoin, this doesn't work. Then we'd have to do this with Ethereum, but we would lose access to Bitcoin, because Bitcoin, out of all the blockchains out there, is the one that can't verify other networks on chain without things like BitVM or OPCats or soft forks. So that's the vision for Bob, using Bitcoin security to get all the other users and all the other assets back onto Bitcoin and to use it in the Bitcoin ecosystem versus having to export and wrap Bitcoin into third-party networks.
Awesome. Well, I'm super stoked for the research and the development, and yeah, very excited about all of this new discussion that we're going to be able to have with the BitVM2 paper getting released. So I want to say, obviously, congratulations for releasing it and being one of the co-authors. I'm super stoked that you were able to be a part of that. And yeah, just, thanks for all your work and contributing to the space. And I know you've spent years thinking about trust minimized bridge design. So it's really exciting to see this initiative move forward. So for everyone listening, thanks for joining today. Shoot Alexei a follow here. You can also follow Bob at build_on_Bob here on X. And you can obviously follow us at Bitcoin Layers on Twitter. But yeah, gonna wrap it up here. Alexei, thank you so much for the time today.
Thanks for having me. And for those interested, I linked the TLDR thread for BitVM and BitVM2 in the comments. That gives like a high level overview. And yeah, if you have any questions, shoot us a DM. Super happy to chat about BitVM2. Thank you. Bye-bye.
Thanks, guys.